그래, 안 되겠지. Hello. So can you hear me? Okay. So let me assume they can hear me. Okay, good.
Okay.
So the today's talk for the field official is particle emission pad. But before I start talking about the pad physics, so let me watch some the slide on image reconstruction. Yeah, so actually that the very basic, as you may know, the basic principle of image reconstruction used in medical imaging is based on this simple back projection. I mean that if we have the object here, like this point source, yeah, actually, the projection profile, in different, the angular direction will looks like this. For example, so in this direction, actually, if we look at the point source from this direction, actually it will be concentrated at the center of this profile. But if we look at this point source in different direction, the center profile will be shifted like that. So in each different projection, the position of the point source will be right. Yeah, but by the way, when we reconstruct the image, actually back project these profiles into the image space in this way. So for example, if we have only the single profile, actually and if we back project this intensity into the image space, we will have this particle. So yeah, with this particular line, we can say this point source exists in one of these pixels, but we don't know yet where this point source was obtained or located. But if we add one more back projection, like actually, and if we add these two back projections, only these pixels will have twice higher pixel value than these other pixels on this line. So actually we can figure out where the point source was. So and that if we add more the back projection lines, actually we have better absolute change. So this is very basic the back projection method that construction. Yeah, but this simple back projection that has some limitation. I mean, actually, this is the phantom, mathematical phantom, and this image is the sine wave. I mean, the accumulated image of the profile, that angular profiles that we acquire. This x-axis, the y-axis is the angle, x-axis is the. So if we generate such a back projected image, so using the same principle that we used in the previous slide, actually we get this kind of very good image. So this is the main limitation of this blurring is the main limitation. Simple calculation. But I think that you may have listen about have heard about filtered backprojections. So then, what is filtered backprojection? Yeah, actually, the filtered backprojection was devised to overcome mitigate the kind of the blurring item. I mean that in the filtered backprojection, we apply a kind of high-pass filter to emphasize the edge information and reduce the smearing of the projection data. Then we back project in such a filtered projection. I mean the filtered projection profile within high-pass filter to emphasize the edge information. Then actually, because of that, high-pass filtering, so the pixel intensity around the object will be on the mean measure. So, and then we can generate it more the sharper image than. So if you compare, this image, you can appreciate filtered backprojection provided much more accurate and matching the sharper images. So this is why that we use filtered backprojection. Yeah, but nowadays in most of the scanners actually we can do this kind of the iterative construction. I mean that the principle of iterative image reconstruction is also based on back projection. Yeah, but it is a little different. In the iterative reconstruction, as you can see here, we start from the images. Actually, in the previous slide, in the back projection, actually we started from the projection space, making this kind of image. But the iterative reconstruction, we start from the initial guess of the reconstructed. Usually, at the first time in the initial data, we just assume very uniform image, very uniform. And then we apply some further projection. I mean that because that we can calculate projections by just accumulating activity in this direction and in this direction, each directions. So we can generate this kind of the side of the projection data. Okay. But that if we assume just very uniform data, actually our estimate that the projection will be much different measured the side of measured projection and scanner spec because we assume just very uniform. Okay. So at the first time that this estimated projection and the measured projection will be quite different. So if we calculate the difference between these images, the error will be quite high. So based on this error, I mean the pixel by pixel difference, actually we can update this the image, the data in the images. Okay. So I mean that if we measure the data is much higher than estimated one, we should do some activity. We should add some activity. But this guy is smaller than this. Actually, we should subtract something, right? So yeah, based on this error, we update this the image space, and then we update, calculate the estimated position again, and compare it to the measured data, and calculate each error. And error is sufficiently small, we can finish this update. But it has the large error, and we should update the position, the images. So we repeat this forward projection and backward projection. I mean, the forward projection, the image space to the sideways space. The backward projection from sideways space to the image space to obtain the reconstructed image. Okay. So this is very basic the concept of the heat. So we use this kind of iterative image reconstruction in almost all PET scanners, especially CT scanners, because the image quality is much better than the filtered back projection reconstruction. And the image, the reconstructed image depends on how many iterations that we did. Yeah, I mean that as you said, usually we start from the very uniform data, but as iteration number, I mean the number of this cycle increase, actually the image will get much sharper than usually. Okay? So the image quality and the image sharpness depends on the number of iterations. So yeah, as I told you, that it has the advantage of better image quality, but the disadvantage of this method is computation time, because in the simple back projection we just need a single back projection. In this case, actually we should repeat forward projection, backward projection multiple times, so it will cause a much longer vision. Yeah, but as I told you, that we can get better images with iterative reconstruction than conventional filtered reconstruction.
The one who stops the iteration, I mean, the one who decided when to stop the iteration, it's the computer.
Actually, that usually, we use in the clinical scanners, we use fixed number of iterations. Fixed number of iterations. So, yeah, theoretically, that we can determine the iteration number. But in the clinic, we just use a fixed number of iterations. Yeah, because that if we apply too many iterations, image start to be noisy. So, too many iterations can cause some noisy data. Number of iteration is pretty. But you should tell your technician what is my favorite number of iteration. You should compare your images based on the number of iteration. You should decide which number is the best. So for example, so in this department, once we buy new machines, actually that we compare different combinations of number of iterations and filters. So the doctor and technician, myself, sit together to determine the kind of image.
So it's different from one camera and the other.
And actually, the optimal numbers will also depend on the subject. But actually, we cannot optimize all the parameters for all subjects. usually vendors recommend some parameter. So from that recommended ones, actually, just to optimize that. Other questions? Then let me move to the PADMI. I think the PAD principle is quite popular, so I think that you already know very many principles. So yeah, so as you know, that in PAD we use the positron emitters, the radioisotope that emit the positron, and that when this positron meet the electrons surrounding the atom, actually the mass of this positron and electron is converted into the annihilation photon. Okay. And actually, this annihilation photons has the same characteristics as gamma ray, and they have the fixed energy. So this is quite different from single photon imaging. So that in the single photon imaging, the energy of gamma ray depends on the radioisotope. So for example, Technetium 99M has 140 kilo electron. Yeah, but in every positron emitters, the energy of annihilation photons is the same. This is very good. Okay, so that is because that this energy was originated from the mass of this electron and positron. Because the mass of electron and positron is constant. We will have that will yield the same energy level. So that is very important. And another important factor that you should remember is that actually these two annihilation photons will the flight in the opposite directions. So actually the angle between these two annihilation photons is almost 180. Okay. Some deviation, very small deviation. Okay. So it is almost 180. So these two factors are very important. And the PET scanner. Then what is the role of a PET scanner? So actually, PET scanner should determine whether this annihilation photons, was generated at the same time, okay? Or two photons are just randomly generated in different conditions. Okay? So that is why that in PET we should use a kind of the coincidence logic to determine whether these two photons was generated at the same time. So once that the PET detector is activated by this annihilation photon, the PET detector each of the PET detector made this kind of trigger signal, square shape trigger. So if that the time difference between these two square signals generated from each of PET detectors, then some part of the signal will exceed this threshold. Then we can say they are coincidence Yeah, but if their time difference is longer than what we have predefined, then actually there some the signal cannot be special. Then we can just say they are not coincidence event, they are independent from each other. Okay. So this is very major piece of coincidence event. Okay. Yeah, so timing resolution in of the PET is very important, very good. So if you have very accurate PET detectors, PET systems in terms of timing, actually you will have better image quality. And if you have PET scanners with worse timing resolution, it will cause so this is because, as I told you, that so we should determine whether this and this is coincidence event one. Yeah, but if my system has very bad time resolution, actually it is very hard to say whether this is coincidence event or this is coincidence. If we have very bad time resolution, we should have the width of this rectangular pulse should be wider than this because there is uncertainty. Yeah, in the case in the case we should use much longer pulses if we have a very bad time. Then it will make random coincidence. So you may know what is a random coincidence. I think let me show you this one. Yeah, so actually this is true coincidence. But we have also many random coincidences. I mean that two gamma ray photons were detected by the PET scanner, but each of them was a single coincidence generated from the different positions. Yeah, but if we have our system has very bad timing resolution, so uncertainty is very high, then we should use larger coincidence window. I mean the width of the scale should be larger. Then we're gonna have it more than so it will cause very noisy. So the timing resolution is so important. Then the current PET systems has usually current systems has less than 1 nanosecond timing resolution, and many of the time of flight PET systems has 500 second timing. 0.5 nanosecond. Then how we can make better PET detectors in terms of timing resolution. Actually, the brighter and faster scintillator enabled better timing resolution, and actually the scintillator should generate the larger number of light photons over a short timing. So this kind of scintillators are such a ones, and the LSO is the most widely scintillation crystals to achieve this. And if the timing resolution of a system is better much, for example less than 100 nanosecond or something like that, actually we can utilize time of flight information. So yeah, so you may know what is time of flight information. So I'm sorry that this is a Korean slide. Yeah, but the time of flight is the difference of the arrival time of two animation photons. So if you can accurately measure the timing difference, actually we can just the pinpoint of the annulation position. If timing measurement is very accurate, okay? Then that you can make point for each of the annulation photon, each of the event. In the case we don't need image. reconstruction. Yeah, but the quantum persistence doesn't have such a real-time resolution. Yeah, but it is sufficiently good for defining this kind of segmentable response rather than this line of response when you back project event that is detected by the test. Okay, I mean we can apply some constraint under the position that these two numeric constraint based on the time of flight and based on the difference in order time to number. So yeah, so that if we have a points here, if we apply back projection based on time of flight information, and we don't have such a timing difference in information, actually so by applying the time of flight image back projection, actually we can use it. So that is why that if we use time of flight information, we can have a better image in terms of. So this is some comparison, time of flight path and line time of flight. So if you compare these two images acquired during the same time, scan time, but with the time of flight information and without time of flight information, so you can appreciate this image has less noise. Okay, so noise level is almost equivalent in 2-minute time of flight per data and 5-minute night time. Okay, so this is because the using the time of flight information put surface in the background. Everything. So the point here is that time resolution is very important in time of flight information very useful to use. Okay. Any question?
Elaborate is that how this line is different from its own. I mean, when any information is placed at the periphery and the two photons reach to a different detector, so this time of flight is able to decide whether these two particular rays which have been approved have originated at same time or not. This is what time of flight.
Yeah, let me say that time of flight means actually that in the conventional PET scan, we just decide whether these two events came together within some timing window. So in the case, the width of this rectangular pulse is timing window. Okay. Yeah. So in the convention, we just use this logic. But the time of flight information means the difference from these two leading edges. Time difference. So yeah. Actually, the time difference between these pulses are different from light. yeah, based on this time difference, actually we draw that segmental class. So for example, in the conventional case, we didn't measure the this time difference. Yeah, but because if we can measure this time difference, if the time difference was 0, then we can say that these two constants was photons were generated around here. Yeah, but actually, let me say this is T1 and T2, and T1 was smaller than T2, then we can say that this was generated. Okay. So yeah, but I mean that if in time of flight we measured this time difference, then we give more information. Original.
The delta T is added to all the signals.
So basically, yes. There are several ways that we take care of time difference each.
Some scanners do say that the newer scanners, they say that we have time of flight. Let's say Philips, they say that they have time of flight, whereas the other scanner doesn't. Say that it decreases the background and increases the signal to noise ratio in balance. But if we don't have a time of flight, maybe we have a better scintillators like LYS or maybe like future, even then the time of flight is required because we have better scintillators. It doesn't have that delta T very high.
Yeah, so yeah.
Like we can compromise.
Yeah, yeah. If we new scintillator has much higher stopping power, so the sensitivity is much higher, then we may not need time of flight information, but the SNR gain by using the time of flight information is for example 3 or 4 for the whole body data. So still the time of flight information will be useful for systems with better scintillators. So the main goal of the development of the scintillation crystals nowadays is to improve the timing resolution. Because that there is some limitation in increasing the tapping power of the scintillating crystals. So by improving the timing resolution, we can get better data. So I think that we should emphasize the importance of the timing resolution.
Advantages of time of flight.
I cannot see the disadvantage. Maybe some computation time. Then let me move to some other physics. So let me now move to the so what is dominant factors that determine the spatial resolution. Actually, that yeah, because we detect the coincidence event. Actually, that the in-principle resolution depends on the position. I mean that depends on the distance from the center. Okay. So yeah, actually, that the PET has the best spatial resolution at the center of field of view, and that the resolution will degrade, get degraded, as the distance as you can see. Okay, so this is one of the factors that we should. And another the physical factor that determine the spatial resolution of pan is this positron range. So we can determine actually the positron range is defined by this distance. I mean that as you know the original position where the positron was emitted, and the where the positron meet electron is a little different. Okay. So the positron meet electron after traveling some distance, and they generate emission photons. So that is why that this position and this position is quite different. Okay. So, but fortunately, that usually this is less than 1 millimeter. But how much this guy can travel depends on the initial energy of this positron. Initial kinetic energy of this positron. So positrons emitted from each different radio isotope have different radar wavelengths. Okay. So, for example, that the positron emitted from the F-18 that we usually use has about 600 kilo electron volt kinetic energy, initial kinetic energy. Okay. I mean that each initial velocity is low. But for example, the positron emitted from the rubidium has about 5 or 6 times higher kinetic energy. I mean that the positron emitted from the rubidium is much better than positron emitted from the rubidium. Okay. So this is why that the positron range of the positron from the rubidium is much lower than fluorine. And the O15 also yield high positron energy, positron range. So this is why that usually the rubidium has lower emission quality. This low positron. So low positron range will cause higher position of something. Make worse images of the okay, spatial resolution. So, for example, so this is the example. I mean that so this is the distribution. Actually, that the positron was emitted at the center of each plant, and actually this the orange dust means the where the positron was the electron to generate the emission. So you can see this distribution is much wider within. Okay. So fluorine 18 has 0.1 millimeter FWH. The distribution of 0.5 millimeter. And this is the relationship between the maximum positron energy and the positron range in terms of ultimate scale. As I said, that the rubidium has the higher the maximum beta energy and longer the positron. So you can see each positron range is almost higher than 2.5 millimeter in length. I don't know. So this is another factor that determine the lead to the degradation in the spatial resolution. So I mean, this is this explains what is the non-collinearity of annihilation. As I said, the gamma ray annihilated in the opposite direction, but that is not exactly the 180. There is some randomness from answer. So every time that this deviation is different, there is some random fluctuation. These directions. So there actually that uncertainty is about plus minus the quarter degree, 0.5. So actually, the resolution degradation of the PET scanner depends on because of this the angular uncertainty, the spatial resolution of the PET with larger the ring diameter is worse than PET scanner with a smaller diameter. I mean that this uncertainty, the position uncertainty due to this angular uncertainty can be estimated in this equation. So if our PET scanner has 80 centimeter diameter, the resolution degradation due to this non-collinearity of annihilation photon is over 2. Like if your scanner has smaller diameter, for example 40 centimeters, actually the effect from this non-collinearity is the more critical. So the spatial resolution of a PET scanner will be determined by such factors. I mean, intrinsic resolution, the detector size, that I explained here. I mean that if you have the smaller detector, smaller scintillation crystals, you will get better spatial resolution. Okay. And the positron ranging and non-collinear. System spatial resolution is this way. Yeah, then what is the main factor that determines the sensitivity of PET? What is the main factor? The sensitivity of PET scanner. I didn't told you that. I didn't tell you. In PET, we don't need to use collimator because the
time sensitive.
Yeah.
Time different.
I forgot to tell you today. That is very important factor, but I didn't tell you. As I said, in PET, we detect two gamma ray photons, two annihilation photons. So we know the direction. For example, if we detect two gamma ray photons, we can say what is this sector, this angle. Yeah, so this is different from the spec. I mean that if we don't have collimator, if some event is detected, we cannot say what was the direction if we don't have a collimator. So that is why we use collimator to reject this line. Yeah, but in PET, because we detect two photons, actually we know what was the direction. So in PET, actually, we just collect this event in the lighted in the same way to generate one prediction data like okay. If we collect all the events that came from in this direction, actually we can generate another projection without use of collimate. So that is why we don't need to use collimate. Then what is the factor that determines time? And timing is also important. Yeah, as I said, the timing resolution determines the image quality, but the timing itself is not the intrinsic factor that determines the sensitivity. Okay. Actually, the timing information, time of flight, improved a kind of effective sensitivity. Yeah, but it is not related to the physical sensitivity itself. Okay. So yeah, the sensitivity of the PET scanner is basically determined by the geometry of the PET scanner. Yeah, for example, so you can detect this kind of light, but you will lose this kind of pulsars light. So if you want to capture this event, you should have a longer schedule, right? So actually, with longer axial length, we're gonna have better sensitivity. With longer axial length, the sensitivity will be higher. Or if you have smaller diameter, with same axial length, actually you will also have better sensitivity. Okay. So the small diameter is better for higher sensitivity. This geometry factor is the main factor that determines sensitivity. Okay. Yeah, but another factor that you should is what kind of scintillating crystal they use. Okay. So each of scintillating crystals used in nuclear medicine has different stopping power. Okay. So yeah, so this is the efficiency of the gamma ray detection. With 2 centimeter scintillating crystals. I mean that so this is for 111 pure electron volt. What, for example, sodium iodide crystal with 2 centimeter length can capture about 50% of the gamma rays. Okay. But the LSO can capture about 80%. Right? So, but in PET scanner we should detect 2 photons. So we need the scale for these values. So with 2 centimeter sodium iodide crystal can capture about 25%. But with the LSO we can capture about 70%. So with the better scintillating crystals in terms of each stopping power. Actually, this is linear attenuation coefficient. So higher linear attenuation coefficient is better stopping power. So that is why that in PET we don't use sodium iodide. We use much heavier and dense scintillating crystals like LSO. But we still lose many. Yeah, actually, that is 50. Yeah, means that yeah, we usually apply energy window as I said last time. So yeah, if we apply some energy window, we will lose more event. Okay. So after applying energy window and we calculate its values, we capture only the event less than 20% of the instance event. Still, we may be balancing. But by the way, this detection efficiency is another factor that determines. So geometry factor is very important. I think this is more. Okay. This detection efficiency is really another important factor that sensitivity.
So it means that the BGO crystal is the best crystal.
Yeah. So in terms of linear attenuation coefficient and detection efficiency, BGO is better than LSO. BGO is better than LSO. Yeah, but the LSO has better energy resolution than BGO. Energy resolution. So if we have a better energy resolution, actually we can detect the scatter better. So that is why that after applying some energy window, efficiency will be similar. And another, the one that we should consider is the timing resolution. So as I said, the timing resolution is very important to get better image. But the timing resolution of the LSO based PET detectors is much better than BGO. Timing resolution. The timing resolution, time of flight information is better with the LSO. So that is why they use LSO because of the time.
The top is only
Sorry?
top is only related to LSO.
Yeah. Yeah, so time of flight is measured by LSO and NISO. Yeah, so yeah, in the clinical, the PET scanners, we use only LSO and NISO time of flight. Yeah, but in the physical research, we try to measure the time of flight information based on the Cherenkov light emission vision. It is very topic that we get. So I already mentioned these event types. Okay. So and let me show you the block detector. Yeah, so actually this is a very conventional PET block detector that we use with photovoltaic tubes. So in the conventional block detectors, 4 photomultiplier tubes are coupled with the temperature crystal arrays. Okay. And then by comparing each signal output, so we can determine the position as we have done in the gamma file. Okay. And yeah, so each of these modules, they kind of block detectors in the clinical PET scanner. So now, if we arrange this in a modular cassette this way, we can make it. Yeah, so yeah, and yeah, so if we have enough time, I think we can learn more about the integration. Yeah, but yeah, let me just say the there are several corrections that we should apply in PAN. For example, we need to correct scattered photons. Okay, so if you can remember, in the gamma camera, we apply some scatter correction based on the energy spectrum. Okay, so we should use the method for scatter correction. Okay, and we should also apply some normalization correction to mitigate the non-uniformity of the PAT detectors. Okay. Yeah, but the most important correction in PAT would be attenuation correction, because without attenuation correction, the image is quite different from the corrected PAT data. Okay.
So in the bottom line and top line, the art is called noise artifacts.
Let me see. Yeah, I think that this image was not corrected for scatter. So yeah, I mean this is due to the non-compact scatter. So I mean that this was not corrected for most of our energy because of the scatter.
And still there are some artifacts bottom right correction.
So you mean that here?
Yes.
This kind of spot. So yeah, actually this is due to noise because of the small number of constants. Yeah, so think about it. Yeah, actually, at the center of field. So coincidence, most of the coincidence is captured by the PET scanning. But at the edge, many of the events will lose because there is no detectors outside of the body. So that is why the sensitivity is very low edge of the scanning.
So it will happen. So my question is, it will happen at the edge, but not in the field which is near the edge.
Actually, if we draw the profile, yeah. So this is PET scanner, and if we draw the sensitivity profile, it looks like this saddle. So at the center, the sensitivity has peaked. Yeah, but at the edge of the PET scanner, sensitivity too high. So noise level will keep at the edge.
Towards the edge.
Yeah.
So it can also happen in a field which is near the edge.
Yeah. In some slices, at the periphery of the actual field, we'll have. So usually in the whole body PET scan, we have multiple bed position. So in each bed position, the sensitivity profile will have this kind of shadow shape. Yeah, but we overlap some slices. So this is why that in the whole body data, the sensitivity profile will usually have this kind of shape. Okay. So that is why only the edge of the end of the slices we can see the kind of.
Is the only way to overcome this problem? There is some other.
Sorry?
This is the only way to overcome this problem?
I think not. Yeah. So because basically image quality of PET is determined by number of how many photons there be. So the best way is to get so yeah, if you really don't like this, just to remove this part. Just to use these images.
And it's not about the beauty of the image. Sometimes there can be some really focal uptake which can mimic a lesion.
So there is a limitations.
Simply,
Yes.
so when
Back to the old strategy.
yeah,
One
your
more thing.
solution should come in the same. I
Less-
agree. Like amputation and other places, you get certain places or manual.
Right.
Better image and less less patient. So yeah, attenuation correction is quite important. And so this slide how we correct attenuation of the patient in the conventional care. So yeah, actually, but that we use the same principle in the X-ray. I mean that to measure the attenuation correction factor, we need two different scans: the blank scan and transmission scan. Okay. So I mean that the blank scan with some external radiation source without any subject, and with subject. So by comparing these two scans, we can calculate attenuation correction factor. Yeah, but in the PET-CT, we use the CT information, like pattern information. Yeah. So this is the attenuation map generated from CT data by applying some filter, converting the CT hospital with the attenuation coefficient from 100 electron. Yeah, we need this kind of conversion because in CT, the X-ray energy is much lower than it is about 112 electron. So do you have any? So yeah, so if we summarize, the spatial resolution of the pan is mainly determined by three factors. I mean the intrinsic resolution of the scanner, PET detector, positron engine, and collinearity. Okay. And the sensitivity is determined by this geometry factor and PET detector efficiency. Mainly determined by okay. Some corrections. Questions. Yeah, but I think this is most important. PET doesn't need any.
If I calculate it in this corrected rate and derivation corrected rate, what would be the difference?
Oh, difference will be very huge. Yeah. Usually, we don't calculate in the S, the number because yeah, it is almost impossible. We cannot determine the calibration factor. Even we cannot calculate the calibration. It doesn't happen. Okay, if you don't have any questions, so next time, the Monday is a holiday. So we have this session in the Tuesday. Yeah, and that I will not be here. So Professor Seo Sung-ho in Gacham University. He is expert in image processing. So he will give me a lecture on processing in the nuclear radiation. Okay, and then next time I will talk about some image quality. How we image.
Can I ask why it's called mu map?
Mu map.